Well, Science, this is Mr. B, and we are going to wrap up acceleration today and wrap up Chapter 11. And this last part is just going to focus on different ways that we can actually use graphs to help us determine what the acceleration is. And that's a pretty useful tool. Graphing is really big now, and again, math and science, just in general. So being able to understand what graphs are actually telling you is a really important skill that you need to have. So we're going to take a look at some different graphs and how they help us understand acceleration and how we can maybe predict the type of acceleration based off of looking at the graph. So the first type of graph we're going to look at, they call them a speed-time graph. So that's going to mean, hopefully you can tell that it's going to compare speed versus time. And how are those going to help us indicate acceleration? And the slope of those graphs are going to be what acceleration is. So make sure you write down slope is what is going to tell us what acceleration is. And again, hopefully you know what the slope of a line is. Maybe rise over run, if you remember that, how much it goes up divided by how much it goes to the side, and that is your slope. So that will also help us determine what the acceleration of an object that we graph is. So you can use a graph to calculate acceleration, like I just said. Graph speed on the vertical axis, so the axis going up and down the y-axis is going to be speed. We always put time on the horizontal axis, which is the x-axis, and the slope is the change in speed divided by the change in time, which again, therefore, is equal to acceleration. So again, slope is rise over run. So our example here, it says this skier's acceleration is positive, and it is going to be 4 meters per second squared. So we know that. Again, we can pick any 2 points and we can figure this out. So if we pick right here, we go up 1, actually this goes by 2, so it's 2, 4. We go over 1, rise over run, 4 divided by 1 is 4. So let's say I picked this point right here and then this point right here. So I go up 2, 4, 6, 8. I go over 1, 2, oh, sorry, yeah, 1, 2. So these, sorry, this graph is confusing. It goes by halves on the side. It goes by 2's up and down. So it's 8 over 2, or 8 up, 2 over. 8 divided by 2 is 4. 12, 3. 12 over 3 is 4. 16, 4. 16 divided by 4 is 4. So they all of those give us the same acceleration of 4 meters per second squared. So that is how the slope can help us graph the acceleration. So all someone did is they took the time, or they measured the different speeds and time of this of the skier. After 1 second, he was moving at 4 meters per second. After 2 seconds, he was moving at 8 meters per second, and yada yada yada, and so on, and that's how we got our acceleration. So that is one way we can use a graph to help us determine what acceleration is. And this example is a constant acceleration, and you notice it is a straight line, and then the slope is the acceleration. This graph is an example of a linear graph in which the displayed data form straight line parts. So that's like the most simple part. When it's just a constant acceleration, it's a straight line, pretty simple to understand. And then kind of on the flip side, there's constant negative acceleration, which it decreases speed. And on a speed-time graph of a bicycle slowing to a stop, a line sloping downward represents the bicycle decelerating, and the change in speed is negative, so therefore the slope of the line is negative. So here's our example. So this first straight line portion of our graph is while the bike is moving down the hill. So right here, the bikers are moving down the hill. They're moving at a constant speed of 5 meters per second. And then once they hit level ground, again, they don't hit their brakes or anything, so they just naturally start to slow down. And again, they are decreasing at a constant speed, so therefore our slope is going to be negative. It's not going up. They're not increasing their speed once they hit level ground. Once they hit level ground, their speed is decreasing, so it's a deceleration. And again, it's still at a constant rate, so it is still in a straight line. So those are, again, this example and this example. Again, that's at a constant acceleration or constant deceleration in this case, and then it's in a straight line. So now we have nonlinear graphs, and this is going to be where a curve connects our data points that are plotted. So linear is straight line, and nonlinear is going to be when a curve connects our data points. So make sure you write that down. That's going to be important. And a distance-time graph of accelerated motion is a curve and the data in the graph are for a ball dropped from rest toward the ground. So it is increasing again in a little more exponential rate rather than a constant rate, which will, again, we've talked about that a little bit. And again, you compare the slope of the curve during the first second to the slope during the 4th second, and increasing slope means that the speed is increasing. So obviously the speed is increasing. Again, it's a little bit of a different rate. It's not as much of a straight line. Again, it is a little more of an exponential, a little quicker acceleration there. And then to wrap it up, they talk about something called instantaneous acceleration, which I don't really know why they didn't mention this with constant acceleration, but again, we'll just wrap it up with our last slide here. So instantaneous acceleration is, again, a lot like instantaneous speed. It's how fast a velocity is changing at a specific instant. So at one point in time, how much is the velocity changing? And acceleration is rarely constant, and motion is rarely in a straight line. So acceleration involves a change in velocity or direction or both. So the vector of acceleration can point in any direction. Its length depends on how fast velocity is changing, and for an object that is standing still, the acceleration vector is 0. So that just kind of, again, summarized a lot of the things that we already learned when we talked about speed and velocity. Again, the rules are pretty similar when we talk about acceleration as well. So that is actually going to be it for Chapter 11. Let me know if you have any questions.